Hello, here I am again, Professor Anita Wasilewska, Stony Brook University, which also is called SUNY at Stony Brook. And here are my lecture notes on Introduction to the Theory of Computation. And the lecture notes are based on a beautiful book, which is called Elements of the Theory of Computation by Lewis and Papadimitriou, a second edition, absolutely, at least my favorite book. So I hope that you will enjoy it as well. And so we are in chapter 4, and that is our last lecture. And we'll talk about Turing machines. And there are 4 parts. Definition of Turing machine. Then we'll talk about computing with Turing machines. And then very quickly about extensions of Turing machines, Turing and Church thesis, and more philosophical problems. And then there is the part which is about the grammars. Grammars are generalization of the notion of context-free grammar to more general grammars. That's why they're called general grammars or rewriting system, and they are much more powerful, and we'll talk about it. So, definition of Turing machine. So, of course, it's called Turing machine because it was invented by Alan Turing in 1936. And here is like a little bit text from Wikipedia. I just want to bring some information that Turing was born in 1912 and died in 1954. Very tragic death, and another story. He was British mathematician, logician, and then because of his work with computability and notion, inventing the notion of algorithm computation and the whole theory of Turing machines, computer scientist. So Turing machine, which can be considered as a model for a general purpose computer, is very computer science. And that's why he is considered by many people to be a father of computer science and artificial intelligence. So automata theory, which we talk up to now, is a theoretical branch of computer science developed by mathematicians during the 20th century. And of course, it deals with logic of computation with respect to simple machines, which we called automata. So, the first description of finite automata, which was called finite state machine, was presented in 1943. Turing was 1936, so you can see the first idea of automata came later by 2 neurophysiologists, Warren McCulloch and Walter Pitts. And then they also did very important beginnings of neural networks because they were neurophysiologists. But so at that, their theory, developed in 1943, was generalized in a more abstract way by Mealy and Moore in series of papers published in 55, 56, and then came the development of finite and push-down automata in a way we did present it, 60s and so on. So we bring it to attention because Turing machine is, in this framework, is the most general and the most powerful automata. course, you could see finite automata, push-down automata. You couldn't do certain things for one class, you did for the other. And Turing machine, first thing we will show that finite automata can't be regarded as a truly general models of computers or computations because they can't recognize such a simple language, and that was our result at the end of the previous chapter. So, and then also today I will show you that, of course, Turing machine is more powerful automata for many reasons, but the first is that it can recognize whatever is the definition of recognition, that language, and much, much more. So, but Turing machines are not automata in our previous sense, but they are similar in design, because that's how it, and also in a sense, people like to thought if you have, these are particular, so they are not exactly straightforward generalization of those two classes of automata. So the main idea is similar to our push-down and finite automata, but so we also have, and here we have a tape, we have finite control like with automata, but now we have also read and write heads, and more things are happening. First, we have a tape which is infinite. We also assume that we have at the beginning a special symbol, so which is called leftmost end of the tape. Not all models have it. Our model would have. It's good to have it. I don't think. So, so it means we can have the models of Turing machine without that, but it's convenient to have. So it's not the original Turing machine. That is a pretty modern model of the Turing machine. And so what happens that the read-write head moves in both directions, reads symbols on the tape, but is also used to change symbols on the tape. So, and Turing machine moves like automata, only one square at a time, and we can visit a finite number of squares during the finite computation. So, finite control at each step performs two functions dependent on current state and symbol scanned by the reading head state. And here's reading head, scans symbol A, and goes to another state. Of course, our delta, the move is described by a function. So function 1, finite control, put the finite control unique in a new state as we did before, but 2, perform or writes a symbol in the tape square currently scanned, replace it by the one already there, or move the read-write head one square to the right to the end. So that you see that the moving head can go right and left, one square. Everything is one square at a time. And of course, we have that end of the tape, but then so end of the tape is designed is signaled by that symbol. And also we have it because we prevent the machine moving head going to the left of the tape. So if reading head reads that symbol, the leftmost symbol of the tape must move to the right. So that is our assumptions. And also we use symbols, new symbols. We use symbols, arrows, because the moves can be to the left, and we have symbol for the move to the right. So we use those arrows, the new symbols, and also you have this extra symbols, which is never erased. And so Turing machine, we put the input, like for example, that would be our input. And then you have infinitely many blanks. And of course, the movement, the whole movement of Turing machine is altering the input, moving, and so on. And also you can write on that unlimited blank portion at the end of at the tape to the right. So now we have a Turing machine. So now we have so that was like we did with automata. You can think about this tape, moving heads, and so on. And now we need to have a mathematical model. And so, and you can see it's pretty similar. Turing machine M is states, alphabet, delta, little delta. It means, remember, capital delta was a relation, little delta was a function, initial state, and we have a special states which are called halt states. And of course, this is a finite set. Sigma is alphabet. Now here, sigma is alphabet and contains, and that's the difference, symbol blank and left and symbol. So these are blank square symbol, and this is left and symbol. So sigma contains those extra symbols, does not contain our arrows. We are using arrows, but, and of course, S is initial state, delta is a function in a second, but H is H is a subset of K, and is called halting states, because the machine can halt. And now delta is important. That's why I want to keep it on the blackboard. Delta is a function which takes state which is not a halting state and element of sigma and go to the state, and here you have sigma arrows. So that's in another state and does something which is element of alphabet, and here is arrows. It means arrows describe the move to the right or the left. And you have condition that delta Q left symbol equal another state B, then, so that is B must be, so it means if you see, if machine sees that symbol goes to another state, it means must move to the right, never go. And 2 is the delta you write of Q A equal P B, where the B is not left symbol. So it's a function which, where B, you can see, is here, so B can be moved to the right or left. So this is a function, so Turing machine is always deterministic. And of course, what does it mean? That here, delta QA equal PB, M in a state Q, scanning A on the tape would enter B, and dependent on B. If B is, you can rewrite, if B is in sigma, you can rewrite A as B. So you replace A as B, or if B is here, you rewrite A by B if B is here, or move to the left or move to the right. And stops, so that is important. M stops only when enters H in halting state. You can see that is not defined on halting states. So the stop is if you assign halting state, its machine stops. And of course, this condition means that if QA PB, when B is not leftmost symbol, it means that the Turing machine never writes never replaces untouchable symbols. And so it means that the guarantee that is this leftmost symbol is well defined as protective barrier. And here is a simple machine example, which I am going. Of course, you have a machine which sigma is A blank, remember, and these are, so really is one letter, blank and leftmost. H is one halting state, and K is two states, Q0, Q1, and H, and initial state is Q0, and here you have a table, Q sigma, like we did, and delta Q sigma. Q0 is initial. A, you assign Q, go to the state Q1, and what does it mean? That delta of Q0A equals Q1 blank. So what does it mean? That in Q0, if the machine looks A, erases A, and goes to another state. Now, what's happening now if in state Q0, C is blank, delta, remember, delta is a function K minus H sigma, right? So you have to define C is blank, goes H, and it means it stops. So if in the state Q0, C is blank, stops, so the computation stops. And now, of course, you have Q0, that is always Q0, our condition. If C is this, so must always goes to the right. And now what's happening in, I am going to remove that. Okay, let's skip it, just to make sure that it's a function, right? So Q0 goes to the right. Now in Q1A, what's happening? Q1 can be empty, on empty, and Q1 on. So that is the same like here. It is Q1 and must go to the right. So this is our condition each Turing machine must have. Now, if in state Q1 sys empty goes to Q0 and moves to the right, and if in Q1 sys A goes to Q0 A. So what really does, it starts and changes A into the empty. So M starts at Q0, changes A to empty, erases A, and goes to Q1. If in Q1 sys A goes back to Q0, and Q0 erases. So Q0 always erases. You need this Q1 as an extra. And then it halts if in Q0 sys empty, it halts, and M in Q1 sys empty goes to Q0 and moves to the right. So now when you look at this, really, when you look at the assignment, Q1A, Q0A is irrelevant because M can never be in a state Q1 scanning A. So this is like a trap state in automata. We need to have it because the delta must be a function. And here you have you can have here's a computation. So it's really erases all A and halts when C's. So it would erase this, and here it would halt when in state Q0 it sees in state Q0 it sees empty, halts the computation. And there's another example, which is a very simple example which is important because has only two states. K is Q0H, and delta Q sigma delta Q sigma, and Q0 sys A sigma is A, and of course always those two extras. In Q0 move to the left, and if Q0 sys empty halts, and if that is always in Q0, if sys end of the tape, this is always Q0 moves to the right. So what it does, if every tape square from head position to the left contains A, M will go to the left end, the tape, and then M infinitely goes between the left and right. So that is the machine which might never stop. And what it does, right? Because if so now we have to do define the computation. So it means we have to define the notion of configuration of Turing machine. So configuration is a little bit more complex. It means you have a state, you have the input, and you have U, where this is element state, and you always put, you see, and you have sigma star, sigma minus empty, and you have E. So what does it mean? For example, you have such a situation. It was similar as it was. that would be a configuration. It means A is at the beginning, and then you have A, B, A. So you can see that on the tape you have this, and then you have, for example, A, and then you have A, B, A. So that is your left side, as we did left, and you look at A, and that is the right, not yet side, not yet red side. So this is similar as we did with automata. And also, of course, you can you can have configuration Q, and you can have the whole W. So that can be, you can have the whole W. For example, B. Let's say that would be the left side. That would be W, and you write that the B is at the end, and that would be the right side. So here the right side would be A. That's another configuration. So that is, and of course the move is between configurations. Now we have a nice shorthand notation. It means we write configuration mathematically is, for example, the triple, right? A, and here is A, B, A, but we write it as Q, because when you look at this, what does it mean? In a state Q, you look at A, you see the head looks at A, and this is the rest of the words on the input. You have BA. So we will write the configurations in this form. Q looks left, and now what is left? BA. BA. So you can see looks at A, and this is right to be read, and that is already read. And in general, you can have a configuration in a state Q. You can have, if you write like this, so it means that that looks here. We look at A. You read already the whole W, and then is unread part to be read. And now what is the move is described by the delta. And the set of all configuration, and we say that one configuration yields to another configuration. What does it mean? The one configuration yields another configuration if one part is replaced by the other accordingly to the delta function. And now you need a little bit more cases, because you have moves. Sometimes it replaces A by B, or move to the right, move to the left, and so on. So you have a little bit more cases. And then you have normal reflexive transitive closure of our transition relation. And then that would be computation of the length n, and we can write it like this, and we have a computation of Turing machine. So, for example, in our first Turing machine, you can, I will just show you just the beginning, that, for example, you have a configuration Q1 A, and I have the delta would be Q1 empty, blank, Q0 move to the right. So looks at this, sees in state Q1 empty, so the next would be Q0 moves to the right, So it means now would look at this A, right? Because the Q, so now you would be looks at A. And now you have to say what it's in Q0 delta. For example, A, that was our first example, goes to Q1 and erases. So the next step in computation would be Q1. That moves, erases this A, replaces this A by empty. So now you would have empty, empty, and now looks at this A, and so on, right? And now Q1 looks at A, what it does, and you can see you have in 10 steps, you get into the halt configuration where all the A's were erased. So that was our machine which would erase A. Okay, now when you remember, the beauty with our finite automata was at the moment when we introduced the diagrams. Delta, all these tables, definitions, computations, the diagrams, you can see better what was happening. So we want to have a similar things for the Turing machines. As we did for the automata, it has to be a little bit different, because even you could see from our two examples, they are extremely simple Turing machines, but the delta was very complicated, and imagine that it gets really too complicated. So we need to have a better way of thinking, as we did with diagrams of automata. So what our graphical representation or diagrams for Turing machines are a little bit more complex. But what we do, we take in the diagrams, we take as the nodes of the diagrams, we take the Turing machine, and then the arc is whatever is happening in between them. So that would be a more complex way. But to do it, we build, like, we will define some basic Turing machines, and then we will describe how you build more complex Turing machines on the base of the basic Turing machines. So that means we use a hierarchical notion in which more and more complex machines are built from simple materials. So at the first moment, we develop a simple repertoire of basic machines together with the rules how you combine them, and then we go hierarchically to more and more complex. So basic machines. So basic machines, we have a machine to symbol, they're called symbol writing machines. So it means that MA is S to states, sigma, delta, S, and halting state, and we put the delta of S B is H A, so in the state which is B writes A, whatever is B in sigma minus, of course you do nothing with that. And so if you have this machine, the only thing the machine does is perform of writing a symbol A, and that's what's called a symbol writing machine. But if A is arrow, we called it head moving machines. And now we can write them, what we have. So it can be when A is a symbol, with A is in a sigma, we write just A instead of MA for the machine, so it's simpler. And also, and this is called A writing machine, A writing machine. And if A is move, we write M, move M, right? But instead of writing here, instead of writing MA, we will write just A. And now for this move, this is move to the, that is move to the right, and this is move to the left. So you have writing machines. You have a machine which moves to the right, move to the left, and that is just a symbol, A from sigma writing machine. And now we have rules of combining the machine. So how we combine? It is in similar way. Let's do the diagram. Here is a simple, let's say you have 3 machines. So we have a diagram M1 and A M2, B M3. So that means, what does it mean? That we have, how we compose. We compose one, this is the rule how we compose machine 1, 2, and 3. And what does it mean? M starts our machine, which we compose. This is a diagram which we, this is our machine M, diagram of M, composed from A M1, M2, M3. It means that starts in the initial starts of M, does everything which M does, until M1 halts. If M1 halts, then if the currently scanned symbol, so if it halts, if currently scanned symbol is A, we initiate M2 and do whatever M2 does. If M1 halts and currently scanned symbol is B, you initiate M3 and do everything. Which MD, you can have 5, 6 machines. So that's the idea, and then you can write a proper definition of that. So that's, so this is one. So that's how we combine the machines. Now let's look at such a diagram. Here, this is your start, right? You start, this is R was M moving. So you have machine which moves to the right, right? So you have machine, R represents machines which moves to the right. And now you have, if it sees this, moves right, goes to the machine which moves to the right. Now, if it sees B or sees A, whatever it sees goes to the right, and the same if sees empty moves to the right. So what it is, you have this machine M consists of two copies of the basic machine R, which is moving to the right. Now we can simplify this, that instead of writing all these pieces, we can write them together. So this is it, put them arrows together, and this is the same machine. So it, right, so if square contains A or B or end of the symbol of the tape or empty, you always move one square to the right. And also if sigma might contain more, right? I didn't say how much. If sigma is exactly all these symbols we put here, if this is your sigma, you can write it just R. R, when instead of listing all elements of sigma. So that means that whatever it makes a copy, R, two copies of R for all elements of sigma. That means it makes two elements of two copies of R for all these elements of sigma. But if the sigma is all those elements, you just skip them. And also another notation, you can write RR instead of writing the arrow or R. And of course you can, three copies would be R3, R, etc. So you have notation, simplified notation. And we'll be using that notation. We've done this.
We've done what?
Yeah, we finished that slide.
Okay, so go to the slide that you're about to start.
Okay, all right, so here.
Okay, so we're going to start with that one.
I don't know what happened.
Gremlins.
Technology.
Gremlins. Okay. 5 seconds. 4, 3, 2.
So now let's look at the like basic simple diagrams, which is of the machines which we will use combine with others. So, for example, let's say that let's make a notation. When you have A in sigma, we write A like complement to say any symbol except all except A. So if you write a machine, a diagram like this, blank. So it means this machine scans tape to the right and what? Until finds a blank, because that is all squares except for the blank, until finds a blank. So that we wrote it as R blank. It means machine which scans to the right until finds blank. Another useful notation is we write here for the same machine A. So it means scans to the right until as long as when A is not blank, so and halts when A equal blank. So it's the same machine written in another way. So now let's look at this diagram and try to read what it does. You see, you have R, and and then A not blank L A. So what it means, that machine scans right until it's blank, so scans until finds not blank, and what it does, copies this A onto the square on the left, goes to the left and writes A. So copies the symbol that in that square into the square immediately to the left where that non-blank was found. And here we have, okay, so our RU that already we did. So these are, now if you have RU, you can have a similar L for L machine. So it means LU scans to the left until it finds blank. Now you have a machine R blank. So what does it mean? Scans until finds not blank. So that would be, is a machine which scans to the right until finds the first non-blank and stops. So that is our non-blank. And the same for left. So that is, so now we have already few of those machines, and we know now how you combine them to more complex machines. So we introduce the Turing machines with the goal that they outperform language acceptors. It means our automata, which we had. So now we have, our goal is to define and examine how they can be used, the Turing machines, to perform tasks of language recognition. So we need some more, as I promised at the beginning. We want to for example, to construct Turing machines which would recognize the language AN, BN, CN. So we need some more policies or some more rules how we put the input on the tape and so on. So first, the input string with no blank symbols in it is written to the right of leftmost symbol. So now input string does not have blank, because sigma can have blanks and other things. So now we say that the head is positioned at the tape square containing the blank between. So it means that we want to start with such configuration. You have start, and now you have beginning of the tape, and head. You always put the empty, and this is the input. So this is called initial configuration M on input W, you see? And also our W is sigma minus, you only have this blank, it's not in sigma. You take away those two things from sigma, and so this W is a real W. Our ABC, sigmas, etc., we excluded those. We only use that blank because as the beginning. So we always input W. If you put input W on a word, like really word as it was for the automata, because sigma now is like in automata sigma, so we always input, this is initial. W, you always put it at the beginning, and you look at W is, before W is a blank. And you look at the blanks, it's called the initial configuration. And now we have a Turing machine, so this is our initial configuration. And now because in automata accepted the word if the computation was finished in the final state. You don't have a final state, you have only half states. So we introduce a Turing machine M, which would have sigma delta S H, where now H, your halting states, denotes if we accept, you halt, but this means this state is called yes. It means I halt and accept the input, and this state we write N because we accept. It means we halt and we reject because N is reject. So we say that M rejects a word if and only if initial configuration yields a rejecting configuration. So you have this, and you have N, and you read the W, so you read W. And of course, now we want to have the language. So we take as our alphabet a subset of sigma minus those two extra symbols. And we want to have well-defined sigma. This sigma can be bigger because we may have a more elements in the alphabet of Turing machine. This is called the input alphabet. So we fix that input alphabet. And we say, so now we have an input alphabet, and we say that, so this is called input alphabet. So you have sigma 0, can be the whole sigma. So it's less equal, minus, this is important. And it's called input alphabet. And you say that M decides language over input alphabet. So you see, this is like our real language because it doesn't have those extra symbols. If for any words, if W is in language, M accepts, then M accepts, then M, okay, I have to, there's a mistake here. If W is in language, then M accepts. M accepts W, and if W is not, and M rejects. So you have, if for W in L, you will get accepting configuration, and if W isn't in L, you get rejecting configuration. And we say, so we know now what does it mean M decides the language, and we say definition that L is recursive so languages if and only if there is Turing machine M that decides it. So these are special languages, of course, Turing invented his Turing machine to give better understanding and an explanation of Gödel recursive and primitively recursive functions, which Gödel invented for his incompleteness theorem. Extremely so that the whole what moved Turing into that model of computation was to really explain which is the difference between recursive function, primitively recursive functions, and so on. So that's why we use the word recursive. So language is recursive if there's a Turing machine which decides that. And then we'll talk about recursive functions in a second. So for the moment, we talk only about languages. So now, if M decides on the language, what does it mean? M decides on the language if started with an input W, always holds, right? That was the definition, and does so in a hard state that is a correct response. So it means that the hard state Y if W is in L, or N if W isn't. But of course, that is very nice. That's what we wanted. But that do not guarantee, no guarantees are given about what happens if the input to M contains blank or left end symbol. So the language is like the pure language. So that one have to remember, because remember the machine can do not halt. And here you have a context-free language which is not recursive. I put it as a theorem because just to make it, because what we promised, our whole goal was to show that we had that language which was not context-free, and the Turing machine would accept it. So you can say that, okay, theorem is the not context language A and Bn is recursive. Or there is a Turing machine. What does it mean? There is a Turing machine that decides that language. So always gives you, so I put it as within in the language of recursivity. And here's the diagram of the Turing machine. Very beautiful diagram. Yes, I leave you to decipher the diagram. The book has a nice, anyway, so that is not for now. We have that, so that was our goal, to show it. Now, as I said, the whole Turing machines he invented the whole apparatus to explain and to give another good explanation. What does it mean, recursive function? And that in Gödel incompleteness theorem, and Gödel invented to prove his incompleteness theorems. He invented the whole theory, which is the field of mathematics, which is recursion theory. And and Turing was the first to explain to people in such a beautiful way what does it mean. So now what does it mean? We say, because now we need to have functions. So we say the Turing machine computes a function. Now you have a function which takes and we say the Turing machine computes a function if for all words W in sigma eventually halts on the input if for all words which eventually halt on the input W, and when it does halt, the tape contains the string FW. So you have W here. The function associates with WFW, and we say that M computes that function if all words on which it eventually halts on W, then when it does halt, the tape contains what that function assigns to W. And we say that the function is recursive if there is a Turing machine that computes. And also, we say the Turing machine semi-decides the language if and only if, for any word, the following is true. Word is in a language if and only if M halts on the input. It doesn't say what does it mean, what L isn't. So then decidability and semi-decidability is weaker than decidability, because decidability gives you yes or no, but here is yes. And we say that language is recursively enumerable if there is a Turing machine that semi-decides the language. So you have, you have a recursive function, and then you will have recursively enumerable functions. So that corresponds to the whole Gödel idea. So now let's look. Just to have a pleasure of writing a theorem. It's not a big theorem, it's a very simple fact. Let's take a language that W contains at least one, language over AB, right? So you have the language which W over sigma is A, B, and the language is that W contains at least one A. And we say is this language L is recursively enumerable. Or other way, it means show a Turing machine that semi-decides L. And here is a beautiful machine. You cannot have a simpler one. What does it mean? Let's go back. It means you start an initial configuration on the input W. So you have initial configuration would be S, right? That's how we W. For some W from sigma star, what it does, it scans to the right until, and this is for everything except of A, right? So scans all except A, you keep scanning, and it stops when A is found. So, beautiful, simple Turing machine. But if A no A is found, it stops if A is found, right? Because it scans until for everything which is not A. So if A is not found, if no A is found, machine goes forever and never halting. So that's why it's only when A is found is semi-decidable. And then we go on, and here are beautiful theorems that we can now prove if we have a lot of the language is recursive. If recursive, then is recursively enumerable. So recursive is the same for the function. The function is recursive, then is recursively enumerable. This is a recursive is stronger property than recursively enumerable. And also, for example, for recursive languages are special, that is recursive, that complement is also recursive. And the same holds for the functions. Now, Turing machine, what we define, as I said at the beginning, we define our Turing machines. It wasn't, and we use it as our standard Turing machines. Original Turing machine from 1936 was two-way infinite tape, was much, much more complex. Yes, when I was a student, I had to deal with two-way Turing machine. So our standard machine is much better. Now, people started to, because to invent, looking for stronger machine, which would be a Turing machine, or easier to compute things. They invented two-dimensional random access machine. Our Turing machine standard is deterministic. So, of course, in natural way, you define non-deterministic machine. So there's, each time when somebody invented a Turing machine, a Turing-like machine, and trying to see if it's not a stronger model than a Turing machine, all models of Turing machine are computationally equivalent to the standard Turing machine, and all known Turing machines are proof that it's that they're equivalent to the standard Turing machine. Now, that's also what is invented, that you have a Turing machine, which is called universal Turing machine. It means Turing machine that is able to simulate over Turing machine. It's called universal Turing machine, or simply universal machine. So that is the looking for stronger, maybe better way of defining our computations. Now, Turing did as that, let's say, visual model, but more mathematically, more logically oriented definition of similar universal nature was given by Alfonso Church, and he used the lambda calculus. And it is intervened with Turing and so on, and led to like two similar, and then of course it's the connection, how you connect the lambda calculus with Turing machines. So finally develop a huge theory of computation field, and they came with what is called Turing Church Turing thesis, that states that Turing machines indeed capture a informal notion of effective method in logic and mathematics and provide a precise definition of the notion of algorithm, mechanical procedure, decidability, and so on. So, of course, it's thesis. It means we believe in it. And of course, the studying abstract properties of the Turing machines yields to insight into computer science as a field and complexity theory and the borders of our notion of what is feasible and decidable and so on. And that is really the introduction. Turing machines, if you do the complexity theory, is the introduction. That's what we did today. It's just a first glimpse, an introduction to the complexity theory and IU. But that is another subject. Thank you very much.